Hi, my name is Lisa Newberger Fernandez, and I'm the lead of Sustainability and Ecosystems for 374 Water. Welcome to the latest in our series of Pioneer Spotlights from Sustainable Futures. Today, I'm delighted to be joined by Dr. Marc Deshusses, co-founder of 374 Water and professor of Civil and Environmental Engineering at Duke University. Our focus today is on new peer-reviewed research just published in October 2023 by the Journal of Hazardous Materials by Marc and other colleagues from 374 Water and WSP engineering firm. This research is about the frontiers of PFAS destruction technologies. But before we get into that, let's start with you, Marc. I'd love to hear, when did the light bulb go off for you on developing the technology that's now at the heart of 374 Water? And how was this the next step in your journey as an environmental problem solver?
Thank you, Lisa. I'm thrilled to be the subject of today's Pioneer Spotlight. Yeah, for this, I need to take you back to 2012. And at that time, this is when I started working on sanitation for less developed countries. And very few people know that actually, over 4 billion people on this planet have their waste end up in the environment untreated. And over 2 billion people don't have a decent toilet. Some of you know the initiative that was launched by that time by the Gates Foundation to reinvent the toilet. And I was in South Africa, in Durban, and at the occasion of a sanitation conference with people thinking about that problem. And we were visiting a sewage treatment plant that was very dysfunctional. And vividly, I can remember. That's why I'm getting in the detail, because very often, you don't quite remember when you have great ideas. And I was at that sewage treatment plant that wasn't working well, with a number of people, including folks from the Gates Foundation. And they were saying, send us proposal. We need new technologies for fecal sludge treatment. And really, just like you said, the light bulb went off. I was like, well, they don't do anything in supercritical water oxidation. And it sounds like, very esoteric. And during this conversation, I'll demystify what supercritical water oxidation is.
Yeah.
But at that point, I had been interested in the technology, and I said, well, I'm going to send in a proposal. And little did I know that, over a decade later, we're here with a commercial product that is destroying all kinds of waste. I did get the initial proposal funded. It was $1 million, and they continued funding for many years at Duke.
It's great to really understand the backstory and where all this is coming from. Let's dive into the research. The title of the research is kind of long. I'm going to read it out to you. It's called Supercritical Water Oxidation for the Destruction of Spent Media Wastes Generated from PFAS Treatment. Okay, there's a lot of acronyms and words in there. Let's start by just diving in and defining or demystifying, as you said, 3 of them. Let's start with supercritical water oxidation. In a nutshell, what are the critical elements of this technology? Can you explain to us kind of the purpose and how it works?
Yes, it is a mouthful. Supercritical water oxidation, or we say SQO. It's also our ticker symbol at NASDAQ, because we're a publicly traded company, as many of the listeners know. So what is supercritical water? We learn in school that water comes either as, and we know from everyday life, that water comes either as a gas, vapor, a liquid that we drink, or a solid, ice that we put in our drinks. Yes. But few people know that there's actually a fourth state of water. And when you heat and you compress water, you get this fourth state, which is called supercritical. It's above the critical point. And that critical point is above the critical point is at 374 degrees C, hence the name of our company, and roughly 220 times atmospheric pressure. You know, in non-metric units, it's 705 degrees Fahrenheit and roughly 3,200 psi. It is a high pressure and temperature, but it's only slightly above what the temperatures and pressures that you see in a diesel engine. What is amazing in supercritical water is that you can do it's a very reactive medium, and you can do very interesting chemistry. And we'll come back to that, but what happens is that you can take a waste that's an aqueous waste, you know, wet waste, like a slurry, like fecal sludge, like this was the idea, or slurries of granular activated carbon or ion exchange resins, or, you know, chemical waste, and bring it to supercritical conditions and inject an oxidant, and we use air, and the organics will all get oxidized. What that means is that they will react, and they will end up in the most stable form: carbon dioxide, CO2, and water, and release the heat of the reaction. I don't like to, you know, it's not a combustion, but it's fairly, you know, in simple terms, you know, you could say, well, you know, it's fairly similar to combustion, but it's done in water, which I find is amazing. But again, it's not a combustion; it's a wet oxidation, and we can do it with all organic wet waste.
And what's the purpose of this technology, or how are we applying it here?
It can be applied to numerous wastes, and it's worth saying that in the industry, wet waste are the most challenging waste, because water is such an amazing solvent, but it also, you know, you cannot burn waste that are wet, and then it poses challenges for processing. But the applications are numerous. You know, we started with the original application, which is you know, fecal sludge treatment for less developed countries, but it applies in our developed countries as well. With the residuals of sewage treatment plants, which are called biosolids. You can apply it to animal manure for industrial farms. Difficult to treat chemical waste, and we'll switch gears or pivot and talk about PFAS in a little bit. But it's such an intense process that it can very effectively treat PFAS, PCBs, dioxin, and you name it. And oftentimes we talk about our systems being omniprocessors, and it's really this idea and concept that we have treatment in a box, and virtually any organic that we feed can get treated.
The second topic that comes up in the title is PFAS. These are commonly known as forever chemicals. Explain to us, why are PFAS called forever, and how is SQO, or supercritical water oxidation, pushing the frontier in PFAS destruction?
I'll keep it relatively simple. You know, PFAS is a class of many hundreds or thousands of compounds formed of carbon and hydrogen and a lot of fluorine. Maybe for some listeners, their chemistry is a little far away, but the carbon to fluorine chemical bond is the strongest in chemistry. It's a very, very strong bond, and that gives PFAS amazing properties. They're therefore extremely stable. And then the chemistry of PFAS compounds allows us to make some amazing things with them. For instance, they broadly use in non-stick, in the synthesis of non-stick materials. The second big use is the use in what is called AFFF, aqueous film forming foams. And in certain formulations with PFAS, and these are used for firefighting. These AFFF, made into a foam, form a film over burning materials. And because the PFAS are so stable, they don't get destroyed by the fire. And because they form a foam around it, they suffocate the fire, and they're extremely effective for extinguishing tough fires. And so in the vast majority of airports, places where you have fuel, chemical industry, the sprinkler systems are equipped with these PFAS-containing AFFF. And as a result of firefighting exercise and their activity, but also the synthesis of AFFF has been released in the environment and is extremely widespread. And we find PFAS literally everywhere. And recently, what has been discovered is that those PFAS, many of them, and some more than others, these PFAS are very bad for human health, and they're very bad at extremely low levels. And we're talking about PPT, for parts per trillion. The motivation for many companies to develop product to remove or concentrate PFAS and to treat those PFAS compounds.
You explained that really well. I've heard PFAS described, or forever chemicals described, as a double-edged sword. It's the thing that makes the chemicals forever, that bond that's both the strength and the weakness. The strength because it is virtually indestructible without special technologies, and the weakness in that as it accumulates in nature, it will not easily disintegrate. So the third topic that came up in the title is about media, and you brought up GAC and IX. Explain to us what does this mean, these filtration technologies, and what's the significance of what's the limitation of GAC and IX in terms of environmental contamination?
Yes. So, first let's define GAC and IX, or this jargon. I hate it when people use too much jargon. So GAC stands for granular activated carbon. Think about the Brita filters, or, the charcoal carbon filters that we have in our houses to remove the taste of chlorine and remove some contaminants. We're talking about such filters at the industrial scale that are installed and being increasingly installed at water facilities. We're talking about the facilities that provide drinking water to our tap. So they are installing industrial scale filters with these granular activated carbon, which will then concentrate the PFAS by attracting and we call it adsorbing the PFAS onto the GAC. Another such medium or similar medium for removing PFAS from the water is ion exchange resin, or IX or AIX, and it's also a solid that comes in little granules, and the PFAS species preferably attach to those granules. So we have these we call them beds or columns, and the water passes to these columns and gets treated. But then what happens is that after a certain time, the GAC or IX is loaded with those PFAS, and it needs to be handled. It needs to be managed. And the big question is, what do we do with those materials? And so we argue that what we need to do is destroy the PFAS. Really, what we need to find are methods that will break this carbon to fluorine bond that I talked about, to eliminate the PFAS and remove it from the environment. Because another, a common means to handle PFAS waste is to put it in a landfill. But landfills create landfill leachate, and those leachate typically are treated in the local sewage treatment plant. And the PFAS we know is going through the treatment process untouched, because they are the forever chemical. They're greatly untouched, and they tend to concentrate in the biosolids, and those biosolids are often spread on land where they can leach and contaminate more drinking water supplies, or those biosolids get incinerated, which doesn't fully destroy the the PFAS, and then it releases PFAS through the air for deposition further in the environment. Or those biosolids get back into a landfill and the circle continues. So we need to break the cycle of PFAS and take PFAS out of the environment. And that's what we provide with our AirSquo system. So the particular study that was just published reports the first time that GAC and IX were treated using supercritical water oxidation. And what we demonstrated through a partnership was the treatment of suspension or slurries of granular activated carbon and an ion exchange resin in a pilot supercritical water oxidation system. And I want to be clear here, the SQO system is an omniprocessor, so we're destroying the GAC and the IX and the PFAS that's on it. It's completely destroyed, completely eliminated, and we mineralize the PFAS, and we break this carbon to fluorine bond, and we convert the organofluorine to inorganic fluoride. We're not regenerating the carbon or the ion exchange resin. It is completely destroyed. The amazing thing is that it destroys all the other organics, all the other pollutants that are on the GAC. GAC is a great medium to take all kinds of organic out of the waters, and then we destroy all of them.
So let me get this straight. You've just said that what's novel and new about this research is that it's the first time that research has been conducted to see how the destruction of media, the spent media, and the destruction of PFAS happen. Explain to us what is the new and novel contribution of this research.
Yes, what we were able to take these different media, make them into a slurry, and feed them at scale. We're not talking about a little test tube, about a little flimsy laboratory system. We're talking about treating these medium in a system that is a good scale and industrially relevant, and completely destroy the GAC and IX and the PFAS that it contains. So it is, on the one hand, it is a proof of concept, but it also paves the way for commercial development and deployment and further demonstration of this technology.
So what would you say is the real significance of this research for 374Water?
I think it's a landmark study, or cornerstone here, because treating slurries is not trivial. We're talking about suspending this material and then pumping it through our systems and showing that it can be completely destroyed. And what this is really transformative. It's not just a small increment in an existing technology. It opens new doors or new frontiers, pushes the frontier of the applicability of SQO quite a bit, because now we can conceive a system where we can take these solids material and dispose of them in a way that is sustainable, is environmentally friendly, and take those PFAS out of circulation. We find an adequate outlet for these materials, which are going to be generated from the treatment of drinking water.
Talked about the PFAS elimination, and in the research there's statistics. And can you put the results of the research into some context in terms of how effective is the elimination of the PFAS and the media? Can you compare it, for example, to the pending EPA regulations or another standard?
Yes, yeah. Um, the destruction efficiency of our air squoze systems is amazing. And what is amazing is that we have many knobs that we can turn to adjust and tune the destruction efficiency. Oftentimes we talk about it in terms of log removals. That means, 99, 99.9, 99.999 percent elimination. And what we found, again, this was in a pilot system that was initially developed for treating fecal sludge. What we found is that we exceeded 99.9% elimination.
Oh,
We know from our studies that again we can tune the log reduction to meet a desired treatment endpoint. Again, not only do we have an amazing destruction efficiency, but we can tune it to a specific endpoint. Now, you mentioned the advisory levels that are set by the EPA for drinking water. They are at extremely low levels in the range of PPT for specific species. And those regulations are advisory levels are being developed. The extremely low levels. And, the question I get oftentimes is, can we reach these levels? So it all depends what you enter with. When you enter with very high concentrations, and it can be several million or hundreds of millions of PPTs, we're probably not going to get to 4 PPT in one go. But what SQUO is very good at is to take a large amount of PFAS, a large mass of PFAS out of circulation. And then to get, if we start with a very, very high level, to get down to the 4 PPT, we can either use a polishing step, the same GAC that is being used for drinking water or ion exchange, put at the tail end of our unit, and when that GAC and IX is exhausted, we just feed it into our system. Or there's schemes where we would extend the reaction or pass it again into our system. It depends. It depends on a case-by-case level. But we are able to get down to these very low level, these single-digit PPT. And I should mention, and sorry for my long answers, I should mention that what is remarkable about AirSquo is that it does that for all the PFAS species. There are some technologies that are around, but sometimes they stall on certain PFAS, or they're not as effective on the short chain PFAS species. AirSquo is effective and destroys and mineralizes all the PFAS, the long chain, the short chain, the ionic species, the non-ionic species, and the precursors. All of them are mineralized. Sometimes we say AirSquo is PFAS agnostic because supercritical water oxidation is such a reactive medium. All the different PFAS react. They react at slightly different rates. We know that, and we understand the kinetics. But at the end of the day, we know how to size systems to reach these low endpoints that are required, and it will do it for all the PFAS. For instance,
well,
it does it as well for super short chain, like trifluoroacetic acid, TFA, or PFPRA, which is a 3-carbon PFAS.
So you've described that SQUO is a very powerful technology. You've also said that it's environmentally friendly in terms of not bringing more materials into the environment, and in terms of energy use. Can you explain what makes SQUO an environmentally friendly technology?
Yeah, so we don't need any chemicals. We don't need any chemicals or consumables. It's basically the waste and air and pressure and heat, and the water that it contains. Uh, and what comes out is very clean. Is the most stable element. It's mineralized. It's CO2, water, and heat. And heat is important here. I should mention that um, the systems that we have were designed with energy recovery in mind.
Mm.
And because of the original intention to be deployed in less developed countries for fecal sludge treatment, the challenge was, can we run the system just on the energy that is embedded in the chemical energy that is embedded in the waste that we treat? So just taking the example of fecal waste or animal waste, we're talking about thick waste, we're talking about concentrated waste. This is where SQO lends itself best. Once the system is started and has reached a temperature, there's enough energy that is released from the reaction, and our energy recovery systems are there to pick up this energy and re-inject it into the process so that the system uses very minimal energy. What you see in my background, by the way, I should have explained it earlier, is our first commercial system. It's called the AirSQO 6. It can treat 6 wet ton of waste per day with very minimal energy input. And we're working on the design of the AirSQO 30, which will treat 30 wet ton a day. And the AirSQO 30, once it's operating, it can run on itself just with the energy recovered from the heat of reaction. That is, for waste that is concentrated, that has the proper energy content. That means it can run off grid. So that's the first component of sustainability. There are many other aspects that contribute to the sustainability feature of the treatments that we commercialize, is the fact that we can treat the waste at the site. And in many cases, transport of waste is a huge contributor to greenhouse gases, just because of the transportation cost in the fuel. And then a lot of treatment technologies were not designed with sustainability in mind. Incineration uses a tremendous amount of generally fossil fuel as energy input. And there's a number of other technologies that are out there, either being developed or existing, which again were not designed with sustainability in mind and use tremendous amount of energy.
So, in summary, what makes SQO so unique? Why is there so much interest in SQO?
Yeah, why is there so much interest in SQO is the fact that it's really this omniprocessor for all kinds of organic waste. And it can do it in a way that no other technology can. It's really transformative. It's not incremental. And it allows us to look at certain waste and say, those wastes can be treated without pre-treatment necessary for other technologies. Or not only can we take care of PFAS, but we can take care of other things that come with the PFAS. We can sanitize the waste, kill pathogens, eliminate hormones, endocrine disrupting compounds, and chemicals, and antibiotic resistant bacteria. It's so good at destroying multiple pollutants at the same time, and it does it very efficiently.
So let's talk about what's next and the implications of this research for 374Water and for this new technology. So first of all, talk to us about the market for spent media, for the filters that now contain PFAS and the need to destroy those. What is the market potential there?
Yeah, the market potential is huge because we now find that PFAS is contaminating a large number of water supplies. It's everywhere because of the way we used it, because of the way we try to get rid of it, because of the widespread use of PFAS and AFFF. And more, we see water districts installing these GAC and IX treatment system. And these systems are very good. They're very efficient. And they treat thousands of gallons of drinking water per minute. But all of them have the same problem. They need to manage those concentrates. And there's a huge market for systems that can handle and destroy the PFAS and those solid media.
And when you think about the research and the findings, what did we learn from the research that is now being used to design the next stage, to design the full-scale applications in terms of size, cost, pretreatment methods, and anything else?
Yeah, so that research really, beyond the proof of concept that we could do it, gave us a lot of information on how to size the system. We definitely need to have follow-on demonstration, and a lot of people are interested in treating their own media, seeing our treatment system at their facilities. And I'm talking here about Department of Defense folks, as well as water district. And so the research was really instrumental in our confidence in treating establishing our confidence in treating that material, as well as understanding the means and the specifics on how to treat these solid media.
The business models, did the research open the door to any kind of new business models in terms of a service model, having a fleet that could go from place to place to handle this spent media?
Yeah, I think we'll give credit to the people who think about business models. I think the research is a scientific paper, but really it gave our folks ideas about, just like you mentioned, developing mobile systems, mobile treatment systems to go and treat the waste on site. The system in the back, the air squid 6, is in a container for easy mobilization. It's transportable, but you wouldn't be moving it, every day or every couple of days to a different facility. But we had been thinking about a system on a back of a pickup truck or inside, a medium-sized truck, and being able to go to different facilities that generate concentrates, not just granular activated carbon, but foam fractionates, reverse osmosis concentrates, and different kind of concentrate. They may have a small or medium volume of these that need occasional treatment every few months, and they may not want to put it on the road and transport it. And there's definitely some interest in development of a mobile treatment system to go and treat those wastes at the sites. It's perfectly conceivable.
What about other types of waste or hazardous waste or soils? I understand that soil is something that is very hard to treat, to destroy, and yet soils can be very contaminated with PFAS and other toxins. What are the next horizons here in terms of types of materials to destroy?
Yeah, soils, I get this question all the time. Can you treat soils? Can you treat soils? Or can you treat this? Can you treat that? So the simple answer is to all these questions. If we can pump it, we can treat it. And that's the problem with soils. Not all of them, but that's the problem with soils, is that it is very difficult to pump soil because of its texture, because of its physical properties at 240 bars, 3,200 psi. We have what is called positive displacement pump. Imagine a piston pump, and if you put soil in there, it's going to abrade the materials and will kill the pump in no time. So currently, we do not have the ability to treat soils. We have ideas about systems to treat soils exclusively. Now, if we dig a little bit deeper into soil treatment, in particular for PFAS treatment, currently how soil is heavily contaminated soil with PFAS is treated is by a technology called soil washing. And it is just what it is. You take soil and you put a large amount of water, you take it and make it into a slurry, and then you extract the PFAS out of the soil, and then you treat the water. And you treat the water by those techniques that we know, the granular activated carbon, other ways. And that works reasonably well. It's not cheap, it's labor intensive, but it does work. For one exception is what is called soil fines. And soil comes in different granule size. And the finest materials, we're talking about grains the size of your hair, so around 40 to 60 microns, 40 to 60 microns is still retains a lot of PFAS. PFAS tend to concentrate in the soil fines, and it's still a challenge for disposal. We actually engage with some partners on projects for showing the proof of concept that supercritical water oxidation can treat soil fines. And because it's so fine, it's far less abrasive than a big grain of sand or a little stone. But there's still work to do. It's at the advanced R&D stage.
Looking at the future, what did the research tell us about how we can improve SQO performance, how we can improve PFAS destruction? Were there any light bulbs that went off in conducting this?
There's still a lot of room for process optimization and condition optimization. The research was an advanced proof of concept. We showed we could treat different materials, but definitely because of the way the research was conducted, there wasn't a deep effort in optimizing the conditions. We have at 374 an R&D lab with a small R&D SQO unit. So it's in the lab and it lends itself very well for adjusting the conditions and conducting experiments under extremely well controlled conditions and systematically investigate conditions. And that is extremely promising for optimizing treatment, not only treatment of GAC and IX as it is in the paper, but treatment of other waste. The lab facilities that we have is also very well suited for feasibility demonstration. If there's a waste that we haven't treated or that someone is interested in obtaining treatment data, that's something that we can do rather rapidly because it's a small system. It can be turned on in a couple hours, and we can run in a very nimble and flexible fashion. And that includes, optimization runs. The lab facility or the lab system is a replica of our largest system, the one in the back, made much, much smaller. And that gives us a lot of process and data intelligence on how we can optimize the process.
So with the lab and perhaps even beyond, what are the next research topics that are in your sights?
Oh, we have a lot. We have a lot on our plate and to-do list. We have a lot of exciting projects and ideas. Without revealing too much, and there's a lot of interest in the food and beverage industry about the SQO treatment, because SQO does best with very concentrated waste, because we need the energy content in order to sustain the reaction, we're looking at the high strength waste. And that's particularly challenging, by the way, to do by conventional technology. So food and beverage is one application. The chemical waste is also one that chemical waste industry is also one that has shown a lot of interest. Island nations, and the reason why island nations are very interested in what we're doing is twofold. Many of them need to export their waste, and in island nations, energy and power is extremely expensive, and that makes our system very competitive and very attractive because we can treat the waste with little or no energy input. But there are many applications, animal waste, space exploration, cruise ships, you name it.
This exploration, now that's something different. Yeah.
Yes, I mean, and we need to think big, and we are thinking big, but definitely when you're putting a human in space, every pound, every kilowatt counts, and having an effective treatment in the box is an asset.
Yeah. Well, the benefit of having a low energy solution that can sit on site where the waste is generated is tremendous. And
one thing here, Lisa, is the fact that we're recovering resources, and we didn't talk very much about it. So we talked about the fact that you feed air, and it's the source of oxidants and the waste. But let's look at what comes out at the tail end of the process. We have clean water, and that water can be recycled. Depending on the input, we get minerals. They fall out of solutions. These are inorganics. And interestingly, one thing that we found is that it contains a very large amount of the phosphorus, in particular when you treat biosolids or residuals from wastewater treatment or fecal sludge or animal waste. It can contain up to 20% of P2O5, and phosphorus is a finite resource, and it's important to recover. So there's tremendous interest in that mineral for use as a fertilizer or as a source of phosphorus. So you get the water, the minerals. There's a harmless vent gas, and that's just a vent gas, but it's nitrogen and CO2 in a concentrated form. Currently, there's a shortage of CO2 in the US, and we can very much conceive a time in the not too distant future where CO2 will be captured and reused, say in the beverage industry, or CO2 would be captured and with some process change, we can capture CO2 almost pure, and can be then fed into some carbon capture and sequestration system for greenhouse mitigation. Despite the fact that most of the CO2 carbon entering the system is generally renewable CO2 carbon leading to renewable CO2. But so the harmless gas and the potential for recovering CO2. And then lastly, heat. Because it's an exothermic reaction. We produce a tremendous amount of heat from the treatment process, from the reaction. And that can be used in HVAC or for drying, or can be reused in different schemes. If you're at a sewage treatment plant that is using anaerobic digestion, although we can replace it, but digesters sometimes need heat, and that heat can be pumped into those systems, or HVAC, as I mentioned. So we see that our system are enabling tremendous resource recovery here. Again, clean water, minerals, heat, and potentially CO2.
Yeah. That's great. What you're describing there is how SQUO is a circular solution. And this is one of the elements that's been recognized. 374Water has been recognized by the World Economic Forum, by the Circulars Accelerator, as a company that is developing circular technologies to recover value from the waste. So that's a really important element for us as we go forward.
Thank you.
Well,
Yes, it is. It is super exciting, and it's great to get these recognition. Absolutely.
Marc, thank you for this great conversation. We've covered a lot of ground. We've gone through the findings of this research. We understand, we've learned some new terms today, some of us probably, and we've talked about what's next. How do we take this research and turn that into new opportunities for 374Water and to push the boundaries of technology and development. My last question to you is, what is the one thing that you hope listeners will come away from this conversation and remember?
Yeah, well, first, thank you very much. I really enjoyed the conversation. The one thing I think is really the realization that this is a novel treatment. We're pushing the boundaries of engineering here, and what this does is really a new way of treating waste and looking at waste as well, because we can recover all these resources. So it is a very exciting time because we can do things that we could not dream about doing, even 10 years ago. So I think it's an exciting time and I'm super excited about it.
Thank you, Marc.
Thank you.